Hi folks, I'm Mr. Fullerton, and I'd like to take a few minutes today to talk to you about types of energy. Our objectives are going to be to calculate the kinetic energy of a moving object, something you've probably done before, calculate the gravitational potential energy of a system, and then analyze the relationship between the work done on or by a system and the energy gained or lost by that system. So what is energy? Well, energy is the ability or capacity to do work. And we previously said work is the process of moving an object. So putting these two together, energy is the ability or capacity to move an object. Now there are many types of energy, and we're going to divide them into two basic types. Potential energy, which is energy of position or condition, and kinetic energy, which is energy of motion. So potential types of energy include chemical potential energy, gravitational potential energy, elastic potential energy, electrical, and even nuclear. While kinetic energy can also be electrical because you have moving electrons in a circuit, light, moving photons, wind energy, moving air molecules, thermal energy, the movement and vibration of molecules, and even sound, the movement of air again. So two basic types of energy that we can break down in many, many different ways. Now, energy can be transformed from one type to another, and you transfer energy from one object to another by doing work. So that leads us to the work-energy theorem. This says that the work done on a system by an external force changes the energy of the system. If I do work on an object, I give it energy. If it does work on me, it gives up energy as it transfers that energy to me. And one way to write this is, if you recall, work is force times distance, and the force has to be in the direction of the distance or displacement, so F cosine theta d, which is equal to the total change in energy of the system. Now, units of energy are the same as the units of work. Since if you do work on something, you give it energy, they have to have the same units. These are known as joules, which we abbreviate with the capital J, not to be confused with impulse, which we also oftentimes write with the capital J. The units, capital J, stands for joules. And 1 joule is equal to a Newton times a meter, but if we break up a Newton into its SI units, we see that a joule is actually a kilogram meter squared per second squared. So all of these are equivalent. Now, let's start with kinetic energy. We've said kinetic energy is energy of motion, so it's the ability or capacity of a moving object to move another object. And we calculate kinetic energy using the formula kinetic energy is equal to 1/2 times the mass times the square of the velocity. As an example, a frog speeds along on his frogocycle at a constant 30 meters per second. If the mass of the frog and motorcycle combined is 5 kilograms, find the kinetic energy of the frog and his motorcycle as a system. Well, kinetic energy is 1/2 mv squared, or 1/2 times the mass of the frog and cycle, 5 kilograms, times their velocity, 30 meters per second. We have to square that velocity to get a total kinetic energy of about 2250 kilogram meters squared per second squared, or 2250 joules. Very straightforward calculation. If we talk about potential energy, that's energy an object possesses due to its position or its condition. The most common, or the one we're probably going to use the most frequently, at least at this point in the course, is gravitational potential energy. That's energy an object possesses due to its position in a gravitational field. And usually we're talking about things like height. If I lift the baseball up in the air, it has more gravitational potential energy the higher it is from the surface of the earth. It has a change in gravitational potential energy. And I can transform that into other types of energy. It has gravitational potential energy now. If I drop it, as it falls, that gravitational potential energy becomes kinetic energy as it speeds up. So how do we calculate gravitational potential energy? Well, to do this, let's think about how we give an object gravitational potential energy. Remember, we said we give something energy by doing work on it. So let's assume we have a 10-kilogram box on the floor. And just as a reference point, we're going to call its position on the floor a potential energy of 0. So, if we do work to lift the box 1 meter off of the floor, we need to overcome the force of gravity on the box, also known as its weight, over a distance of 1 meter. Therefore, the work that we do in lifting this is going to be force times displacement. They're in the same direction, so the angle between them is 0. Cosine of 0 is 1. So we can just use work equals force times displacement. The force we have to overcome is the weight of the box, its mass times the gravitational field strength, or acceleration due to gravity, times the height we lift it to, its change in height, or 10 kilograms times 9.8 meters per second squared times 1 meter, for a total of about 98 joules. So to raise the box to a height of 1 meter, we must do 98.1 joules of work on the box. The work that we did in lifting the box is equal to the change in the box's gravitational potential energy. So once it's 1 meter above the ground, it has a gravitational potential energy that's 98 joules higher than when it was sitting on the ground. So we transferred our stored energy to the box by doing work on the box. Now the change in the object's potential energy, delta potential energy, gravitational, is equal to the force of the gravity on the box times its change in height, mg delta h. So we have derived the formula for change in potential energy. Pretty straightforward. Potential energy due to gravity is mass times acceleration due to gravity times the change in height. So let's take a look at a sample problem here. The diagram shows a 155 Newton box on a ramp. An applied force causes the box to slide from point A to point B up the ramp. What is the total amount of gravitational potential energy gained by the box? And right away I look at that diagram and see lots of numbers and go, that's looking pretty complicated. But all we have to realize is the change in potential energy only depends on the height of the box. So the change in potential energy, gravitational potential energy, is mg delta h. In this case, we're given the weight of the box, mg, is 155 newtons, so that's going to be 155 newtons times its change in height. It started at level 0 and went up to 1.8 meters, so its delta h, change in height, 1.8 meters, gives us a total gravitational potential energy change of about 279 Newton meters, or joules. Really straightforward problem when we think back to what's really important here, the definition of gravitational potential energy. Let's look at another one. Which of these situations describes a system with decreasing gravitational potential energy? A girl stretching a horizontal spring, a bicyclist riding up a steep hill, a rocket rising vertically from the earth, or a boy jumping down from a tree limb? Well, if you notice, the first one involves stretching a horizontal spring. That's going to be elastic potential energy, which we'll deal with when we talk about springs. Bicyclist riding up a steep hill or rocket rising vertically are both having increasing gravitational potential energy. The only time where we have decreasing gravitational potential energy is when the height changes, when the height decreases, the boy jumping down from the tree. So the correct answer must be number 4, a boy jumping down from a tree limb. Let's take a look at one more. A hippopotamus is thrown vertically upward. Not quite sure how you throw a hippopotamus, but if you do, you'll know how to analyze it from an energy perspective. Which pair of graphs best represents the hippo's kinetic energy and gravitational potential energy as functions of its displacement while it rises? Well, we have to remember, as the hippo rises, it's going to start with the fastest velocity, slow down, slow down, slow down, slow down, stop at its highest point on its way up. So it's going to have the most kinetic energy initially, and that kinetic energy is going to get lower and lower and lower and lower. At the same time, it's going to start with a very low potential energy at its lowest point, and as it has a higher and higher altitude, higher and higher height, it's going to get a larger and larger gravitational potential energy. So we need to look for graphs where we have a decreasing kinetic energy and an increasing potential energy. That happens right here with number 1. The object's kinetic energy decreases as it slows on its way upward, and the hippo's potential energy increases as its height increases.